Welcome to Unit 3, Collecting Data. In this video, we're going to focus on the topic 3.5, Introduction to Experimental Design. All right, let's do a quick recap of what is an experiment that we learned in previous videos. In an attempt to see if an explanatory variable causes a change in the response variable, researchers impose treatments of the explanatory variable onto subjects to see if there is a change in the response variable. So if you're ever unsure if you're reading an experiment or an observational study, the number one thing to do is to think what the explanatory variable is and see, was that explanatory variable imposed or assigned to the subjects, or was it something that they made a decision on their own? If it was assigned or imposed, it's definitely an experiment. Now remember, a couple facts. Only through a well-planned experiment can a cause and effect relationship be found. We don't just observe, again, we impose or assign on the treatment. And keep in mind that variables can either be categorical or quantitative, or any combination. They could both be quantitative, both be categorical, or there could be a mix of them. But I want to go back to that cause and effect one more time. An experiment is the only way to show a cause and effect relationship. But keep in mind, that doesn't mean that every experiment will show a cause and effect relationship. Sometimes at the end of an experiment, you might learn that there is definitely a very strong relationship between two variables, but you still might not be able to say that one causes the other. Maybe you learn that there is simply a very strong association. But if you do want to show a cause and effect, an experiment is the only way to go. All right, when you make a good experiment, it's got to be well planned out, and it's got to contain several key components that we're going to go over. Now, there are some aspects of an experiment that are optional, meaning that they could be in there or they cannot be in there, all depending on the necessity of them based on the particular problem. And we'll examine some of those at the end as well. Keep in mind, even the best, well-planned out experiment still could have results that show no relationship. So just because you think you have the best experiment in the world doesn't mean it's guaranteed to show that X will cause Y. All right, so the first aspect of an experiment I want to explore is who. Who is involved in an experiment? Three major groups. We have the researchers. These are the people who are planning the whole thing. They know everything and make the experiment good. Hopefully they make the experiment good. The experimental units, these are the individuals, which may be people or objects, that are assigned treatments. When the experimental units are people, we usually do call them subjects or participants. But if you're going to give a group of people something, 50 people get this, 50 people get that, they are the experimental units. If it's objects, like these 50 containers will get this, these 50 containers will get this, these 50 containers will get this, then the containers are your experimental units. So what or whoever is getting the treatment are the experimental units. Now the evaluators are a part of the research team, but the evaluators are people that are hired by the researchers to collect or measure the response variable from the experimental units after the treatments have been handed out. So whoever's actually going to measure or evaluate the response are your evaluators. Now the reason why I don't lump them into the researchers is because usually we want the evaluators to be independent of the researchers. We don't want the evaluators to have any bias, like maybe they want the experiment to show something, so they'll kind of lean towards one way, or they'll maybe lie about the results. Now that's something that obviously should not happen, but to prevent that from happening, we usually want our evaluators to be independent. We don't want them to know anything that's going on. They're simply going to do some measuring at the end of the experiment. All right, also important in an experiment is to know what the variables are. An explanatory variable, also called a factor, in an experiment is the variable whose levels are manipulated intentionally. So we might give out different treatments or different amounts of the treatment, but that's the explanatory variable. So if I'm going to give some people a nicotine patch to wear to quit smoking, and other people are not going to get the nicotine patch, well, the explanatory variable is the presence or absence of the nicotine patch, and it comes in two different levels, nicotine patch or no nicotine patch. The level or combinations of levels of the explanatory variable are called treatments. Now, you could have more than one explanatory variable in a problem. Like maybe you're doing some cooking and you want to know what's the best time and temperature to cook something. Well, then you got to play around because you might have some different combinations. Like you might have 10 minutes at 300 degrees, 10 minutes at 350 degrees, 10 minutes at 375 degrees, and maybe you have 20 minutes at 300 degrees, and so forth. So you're going to have some different combinations of your two explanatory variables in that case. Now, a response variable is a variable in an experiment. It's the outcome from the experimental units. This is something that we measure after the treatments have been administered. This could be something that we measure or something that we just simply ask. Again, it could be categorical or quantitative. All right, now there is one more super important variable, and that is a confounding variable. A confounding variable in an experiment is a variable that is related to the explanatory variable and influences the response variable. And this may create a false perception of an association between the two variables. So because there's this third variable somehow related to both the explanatory and the response, then we're not really sure. Did the explanatory influence the response, or did this other confounding variable? So keep in mind, we do not want confounding variables. They are often present in observational studies, which is the primary reason why observational studies cannot show cause and effect. Remember, in an observational study, you're simply just observing, so you don't have any control at all, and that's what allows confounding variables to be confounding. To better understand confounding variables, let's look at an example. So, about 18 years ago, researchers collected surveys from 260,000 individuals, so lots of individuals, 402,000 almost, right? A lot. Respondents were asked how many cups of coffee they drank each day, and after 15 years, researchers checked death records to see how many of those respondents had died. Their findings were that respondents who drank 2 or more cups of coffee per day were 10 to 16% less likely to have died after the 15 years, as opposed to respondents who didn't drink coffee. All right, well, the explanatory variable is coffee. I didn't give people the coffee, so this is not an experiment. All we did was we asked them how many cups of coffee they drink. That's not assigning or giving, that's just asking. So this is clearly an observational study. And like I mentioned, observational studies have lots of confounding variables. So what else could determine when somebody dies besides drinking coffee? Well, I came up with a long list here. And the important thing is that everything in this list could be tied to both the explanatory, drinking coffee, and the response, dying. That is a true confounding variable. So for example, age. Young people may be more likely to drink coffee than old people. So coffee drinkers may be less likely to die because they are younger, not because they drink coffee. So age. Younger people might drink coffee more, and younger people are going to live longer. They're not going to die after 15 years. So that is what happened there. So that one variable was tied to both the explanatory and the response. Income. Wealthy people may be more likely to drink coffee than poor people because they can afford it, right? If you're poor, maybe you can't afford to drink 5 cups of coffee a day. So coffee drinkers may be less likely to die because they are more wealthy, not because they drink coffee. And if you think about it, income is also tied to how often you die. There have been a lot of very good studies that show wealthier people live longer because they can afford medical treatment if they need it. So that's a variable that is related to both drinking coffee and dying. Exercise. People who exercise frequently may be more likely to drink coffee than people who exercise less frequently. So coffee drinkers may be less likely to die because they exercise more often, not because they drink coffee. So again, if you exercise a lot, you might be the type of person who needs energy because you like to exercise. So you drink a lot of coffee. But because you exercise, you're healthy, so you live longer. So that is a variable that can be related to both. So the idea here is that we cannot conclude anything from this study because we don't know about all these other confounding variables. Maybe we see that there is an association, but we cannot say that drinking coffee causes you to live longer because this was not an experiment. Now, there is another type of variable that I briefly want to mention, and that's a lurking variable. A lurking variable is typically something that you can fix, right? So a lurking variable is something that only affects the response. So it's a variable that definitely could change the response besides your explanatory, but it's something that is fixable, something that you can control for, and I'll talk a little bit more about that when we look at some examples. A confounding variable is something that you literally cannot do anything about. I can't do anything about age, income, or exercise. It is what it is. I can't make somebody have a certain income or be a certain age, And that's why those are true confounding variables, because they relate to both the explanatory and the response. All right, let's dive now into the 4 major aspects of all good experiments. These are called the 4 pillars. So the first of the 4 pillars is comparison. All good experiments have to at least have 2 treatment groups. Now, one of those 2 groups could be a control group that gets nothing. So for example, if you want to know if a new pill is going to help reduce somebody's headaches, well, then you have to give a group that gets the pill and a group that doesn't get the pill. That group that doesn't get the pill would be your control group, but you have to have at least 2 groups. Now, if you're doing an experiment that simply wants to see, does Tylenol work better than ibuprofen at reducing headaches, well, then you don't need a control group, because you already have your 2 groups, and all you want to do is compare Tylenol to ibuprofen. You don't really care, or you already know that taking neither of them won't help. So you don't need a control group in that case. So control groups are only needed if you only have 1 treatment group, but you know you need a second. All good experiments also need random assignment. And this is when we determine what experimental unit gets what treatment. That has to be determined randomly. I cannot let my subjects pick which treatment they get, nor can I pick it for them. It has to be completely random. So what container gets what person gets what animal gets what, has to be chosen randomly. Replication. Replication is the idea that you have to have more than 1 subject or experimental unit in each treatment group. You know, if I only have 1 person in each group, there are a million reasons why one person's headaches go away than compared to another person, right? There are far too many lurking and confounding variables when you only have 1 person. But if you can show that something works for 100 people, that is so much stronger than showing it works for 1 person. The 4th and final aspect of all good experiments is control. These are controlling for those possible lurking and confounding variables where appropriate. Sometimes you just can't control things. So a couple more notes here. The researchers must control for all the confounding and lurking variables that they are aware of and have thought of. Randomization helps control for all the other confounding variables that researchers can't do anything about. And I will address that again if you're confused on that. All right, let's talk about comparison really briefly. It's a pretty easy pillar. All experiments have to at least have 2 treatment groups. You only need a control group if 1 treatment of the explanatory variable is there, hence a second group is needed. Control groups are great to have because they act as a baseline. So even if I am looking at Tylenol versus ibuprofen, I don't have to, but it couldn't hurt me to also add in a control group that gets nothing, because maybe I find out that actually doing nothing for a headache is better than taking Tylenol. You never know. So having a control group is important, but it's not a necessity if you already have 2 groups to compare. All right, randomization. I cannot tell you how important randomization is. Most people think that randomization just sounds like, oh, I get it. Who gets what has to be done random. It just sounds like something that needs to be done. But there is a very specific reason for randomization that I want to go over right now. What we want when we create our treatment groups is we want 2 or more groups that are very, very, very similar. The only thing that we want to be different about those groups is what we assign them. So if I'm going to make 3 random groups of people, 50, 50, and 50, I want those groups to be very, very, very similar. And what I mean by that is I want them to be very different within, similar between. And I know that that's a tough concept to explain, so let me try to explain it. I want the 50 people in group 1 to be a complete mix. All different types of people, right? Very different. Young, old, exercise, don't exercise, healthy, not healthy. I want them to be very mixed up. And I want the other groups to be very mixed up as well. So I want them to be very different inside, but similar between. So I want all 3 groups to be similar in the sense that they are very mixed up and different. Because that's what randomness should do, right? If I'm going to truly make groups at random, I'm not doing it based on gender or anything, right? I'm literally making it random. And if you do something completely random, statistics tell us this, you should get nice mixed up groups. I should have groups that include boys, girls, young, old, exercise, don't exercise. everything that I mentioned. Okay, so here's the kicker. Random assignment tends to balance the effects of uncontrolled confounding variables so that the differences in responses can be attributed to the treatments and nothing else. So here's the deal, right? The reason why randomization is so important is because I want those confounding variables to be in all groups. For example, age. Age is always a confounding variable, especially if you're doing something related to drinking coffee or smoking, right? But the idea is that if I have different ages in all my groups, well, then it's no longer a confounding variable because you can't say that group got better because they're all young people. No, they weren't all young people. It was a mix of young and old people. In fact, I had a mix of young people in all the groups. Another confounding variable that is present in a lot of studies is exercise, right? Some people exercise, some people don't. Well, true randomization should put people that exercise and don't exercise into all groups. That way somebody can't say, oh, that group got better because they exercise a lot. No, they got better because of my treatment. That group contained people that exercise and don't exercise. It didn't matter at that point. So if we allow randomization to evenly disperse all of those confounding variables into all of my treatment groups, well, then it no longer is a confounding variable. So, some people think that confounding variables or lurking variables lead to bias, but they don't because of randomization. If I allow those variables that I cannot control for to be evenly dispersed into all of my groups, then I have made 3 really, really good mixed up groups, which will allow only my treatments to tell me what changes in the response. All right. Now, there are 3 different methods for random assignment. I hope you now understand the importance of random assignment, but we have to understand how to do it. Well, these are the same 3 things we saw earlier with a simple random sample. 1, we could give everybody a unique number and then use a random number generator to select my numbers. And the first 30 go into group 1, the next 30 go into group 2, and the remaining 30 go into group 3, something along those lines. I could also give everybody a unique number and then use a random number table to pick my numbers for me so I know who goes into what group. Or at the end of the day, I could give everybody a unique number, place those numbers into a hat, and pull them out. The first 15 names go into group 1, the next 15 group 2, and the remaining 15 go into group 3, all depending how many people you have. So it's a very, very, very simple way of doing a random assignment. Please make sure if you're asked to do this, you pick one of these 3. All right, why is non-random so bad? Well, if the subjects get to select what treatment they get, that self-selection could become a confounding variable as to why the response variable changes for them. For example, motivation could be possibly one of the worst confounding variables. If a person picks something that they think will help them, then they will be motivated to get better, and maybe the motivation alone will help them get better. Or some people might select to go into a group with their friends, and they're going to do what's comfortable with their friends, and being with their friends or doing what's comfortable is what allowed them to get better. That becomes a confounding variable. So how do we combat this? Again, make it random. You can't control that there are people in this world that are motivated and people in this world that are unmotivated. But if you truly do it random, you should put those different people in all of the groups. So each group will have people that are motivated and unmotivated. And at the end of the day, because your group is nice and mixed up and truly random, the only thing that's going to affect that group is the treatment you give them. All right, replication. This is really easy. All you have to do is make sure that there is more than one experimental unit or subject in each group. Anything more than 1 is better. 2 is better than 1, 3 is better than 2, 5 is better than 3, 10 is better than 5, 20 is better than 10, and so forth. The more replication you have, the more subjects that are in each group, the better. If I could show that a variable works for 100 people, then it's far more of evidence than if I say it works for 10 people. And I could even say the same thing for 1,000. If I could show that my new pill works for 1,000 people in that treatment group compared to 1,000 people that were in a control group, that is even stronger evidence that my new pill works. So replication is having as many people as possible. Anything is more than 1. All right, finally, control. This is a big one. It's the job of the researcher to make sure that all treatment groups of experimental units or subjects get treated the same, except for the different treatments they are given. All right, take time to address all possible lurking confounding variables and control for them. For example, my nicotine patch that I'm going to use to help people get better. I can control how long they wear it for. I don't want how long they wear it for to be a confounding variable, so everybody wears the nicotine patch for 3 months. Or where on the body the nicotine patch goes. Well, where it goes could be a confounding variable, so everybody puts it on their upper right arm. You want to make sure that your groups are treated and are as similar as possible, except for the treatments that are given to them. It's your job to have the control to make sure that happens. However, please keep in mind, and I've mentioned this 4 times now because it's so important, is that there's oftentimes variables you cannot control for. And bingo, that's where we let the randomization process evenly disperse those variables into all the treatment groups. So like age, exercise, gender, once again, I can't control for those things. And that is where you make sure randomization evenly puts them into all groups. Is it going to be perfectly even? No. But that's okay. That's part of truly being random. All right, here are a couple additional aspects of an experiment that, again, are smart to think about, but sometimes can't always be applied. Single blind experiment. Here, the subjects do not know which treatment they are receiving, but members of the research team obviously do. So here, the idea is, what am I getting? I don't know. I have no idea what I'm getting. And that's me being blinded. If I'm going to be taking some different pills, and the researchers know that some pills are Tylenol, some pills are ibuprofen, I should not know what pill I'm taking, because then it could lead to bias. If I have heard through my friends that Tylenol works better, well, if I know I'm taking Tylenol, I might think I feel better, and the thought process of feeling better will make me actually feel better. A double-blind experiment is where both the subjects and the evaluators doing the measuring do not know what treatments they are given. The idea here is whoever's doing the evaluated should also be blinded. Now, you might think that that's stupid and unnecessary, but I don't want that person to potentially have, a reason to lie, right? If I am running the experiment and I really want my explanatory variable to work, and then I end up doing the measuring, I might be biased and I might, ask a person and I'll say, oh, I noticed you used Tylenol. Oh, I bet you're feeling better, aren't you? And I might mark down that they're feeling better, but they really weren't. And that would lead to a ton of bias. So the evaluators should be blinded as well, if it's possible to blind them. Let me give you an example of blinding that really kind of demonstrates why it's important. I read an actual study that took 20 patients that had chronic knee pain. All of them went into the hospital to get surgery, but only 10 of them were actually given the surgery. The other 10 were cut open. Their knee was cut, but they did not actually do anything into their knee. They didn't clean anything. They didn't fix anything. So 10 patients actually got the knee surgery. 10 certainly thought they did. And they were all blinded, right? Everybody went home and thought that they got something. And the craziness is that the results showed everybody felt improvement. Everybody went home thinking that they got the surgery. And 3 months later, when they were asked, how's your knee pain? Everybody said the knee pain went away. So that just goes to show that the pure thought of having surgery made the knee pain go away. It was an absolute crazy experiment, but it really shows that blinding the subjects is important. Because if those 10 people went home knowing they got nothing, hey, thanks for being a part of my study, you're not going to get the knee surgery, that knowledge, oh, that's stupid. My pain still hurts. My knee hurts a lot. In fact, it hurts worse. That could happen if you don't blind your subjects. All right, one more topic here, control groups and placebos. When working with people and a control group is given where no treatment is typically given, we think that we should, or it's typical that we give a placebo, which is a fake treatment. So when you're working with people and you're going to give a control group that gets nothing, you need to give them a fake treatment. The reason we do this is to control for the placebo effect. And this is exactly what I was talking about with the knee surgeries. The placebo effect is the idea that when people know they are in an experiment, that attention might give them extra motivation or an extra expectation to see an improvement. It is completely natural, right? This happens in all humans. You cannot get rid of these expectations. When a person knows that they're involved in an experiment, they naturally are going to have this expectation that they're going to get better. But what you could do is give them a placebo to a control group. That way they're blinded and everyone at least thinks that they're being a part of the experiment. So the placebo effect has actually nothing to do with the placebo, and I'll explain what I mean by that in a moment. The placebo effect is simply this naturally occurring thing in human beings that when they're involved in an experiment, they instantly have an expectation that they're going to get better. They have motivation to get better. And if I take that motivation away, I just create a confounding variable. So if I send people home and I tell them, hey, sorry, you're not going to get anything. Well, I just created a confounding variable because now those people no longer are motivated or having that high expectation to get something. You actually cannot get rid of the placebo effect, but you can control for it by making everybody feel that they are a part of the experiment, and you do so with a placebo. Now, you do not need to use placebos with animals or objects. And if a control group that gets nothing is not needed, then neither is a placebo. So if all you're doing is comparing Tylenol and ibuprofen, you don't necessarily need a placebo unless you want to. Again, it's kind of your option, right? As long as you already have your two control groups or your two treatment groups, excuse me. So, a lot of kids kind of don't always necessarily know what a placebo is. Most people do remember it's a fake treatment, but they don't always understand why it's needed. And it all comes down to this attention of an experiment, right? Motivation is always a confounding variable that is hard to get rid of. So what you could do is make everybody motivated to get better. Now, who knows what your results are going to be with that, but you can't have some people motivated because they know they're in their experiment and some people not. Now, placebo is optional. If there is no way for you to hide what they're getting, well, then what could you do? An example that we have seen is what's better at helping kids learn their math facts? Computer programs or flashcards? Well, I can't blind those people, right? I can't give a fake treatment. I can't give a placebo. There's no fake treatment for learning math. I mean, what can you do there? But everybody is getting something. Everybody thinks they're in the experiment. Everybody knows they're either going to get the flashcards or they're going to get the computer-based programs. So everybody does feel motivated. Everybody does feel part of the experiment. So that's why there's no need for a placebo there, because I literally can't give a fake treatment in that situation. So again, this is one of those optional things, but it does kind of go under that main pillar of control, because remember, you use a placebo to control for the placebo effect. Not get rid of it, just let everybody experience the placebo effect. And that's what we use placebos for. All right, that's it for experimental design. I will say that there are a couple more videos coming. One is going to show you some examples, so that way we can actually see everything we learned in examples. I would highly recommend watching that. And we're also going to learn a couple different ways that you could design a really good experiment. And that's also coming, so pay attention for those videos.